You know the Pit and Pendulum? It's a poem by Edgar Allan Poe. You're in the pit and the wall starts closing in on you, right? I keep getting closer and closer. Now, suppose, here's the intellectual problem. Suppose, I can't draw on the floor. Suppose I'm actually getting closer and closer to this point here. Here's a point. You can't, here's the intersection of those lines. I'm actually closing in. Now I'm going to make the fundamental leap of logic that connects the problem of area with the problem of the number. I'm essentially going to that point as I keep getting closer and closer, but maybe like the square root of 2, that point isn't there. It isn't there. Maybe there's a manhole there, an infinitesimal manhole, and as if I actually do, at each stage, do I actually ever reach the circumference? No. No. It's always going to be greater than the circumference, so at any finite step in which I'm moving, I never actually reach that point. So, but maybe there's a manhole there, maybe there's a hole, and if I actually could reach it, I'd fall in. There's no, so in other words, what the Greeks couldn't answer was in this process there was actually what we would call a limit. That somehow there wasn't a hole at that point in which I'm reaching. But they just bypassed that because they had a belief. You just don't worry about whether it exists, like the kids, no kid worries about the square root of 2. You tell them it exists, they're happy. The system tells them it exists, so they believe it exists and they worry about the hole being there. So this is exactly the same. You could do this with the square root of 2. You could find, the Pythagoreans could find a set of steps of rational numbers, of fractions, always moving to the right, getting closer and closer to what ought to be the square root of 2, but maybe it isn't there. And the Greeks never resolved this issue. What happened is, after the decline of classical Greece, people like Archimedes and Apollonius and Heron and all these other, they just completely ignored it, just like we do today. Simply don't worry about it anymore. We wish it away. So you go ahead and happily calculate everything. This became a very, very serious problem later on when it was realized that when they developed the calculus is the science of calculating instantaneous velocities. It was until Newton in the 17th century, instantaneous velocities, even the idea, there was no definition of what an instantaneous velocity is, like the velocity of your car. And there were the same kind of pit holes. People found these kinds of logical gaps over and over and over again. And Newton and Leibniz were attacked on the basis of the fact that their whole system of calculating instantaneous velocities of objects in space, of cars, of wagons, or of anything, was full of logical holes. Okay. Now, but we have this leap of faith that that hole doesn't exist. So therefore, the sum of these lengths has to get closer and closer to the circumference. Once we have that, we can see that the circumference, the ratio of the circumference to the diameter must be a constant. So let's do that. So what I'm going to do now is I'm going to erase all of this here. So we know what the circumference is. It's the number that these sums march towards as the number of choppings gets what? Greater and greater. It's a leap of faith. The leap of faith is that there's no hole there, that that number exists. That as you're marching towards nothing. Okay, so now let's take another color. Here, let's take orange. I don't know, I've used orange before. This looks pink, but I think it is pink. Shocking pink. Okay, so now we go like this. Ooh. Okay. So now I want to give a name to the radius. It's the little radius, so let's take the little circle and call its radius little r, because it's the little circle. Now I want to downgrade the circumference of the little circle to what? To little c. Little c is the circumference of the little circle, little r is the circumference of the, I almost tripped over that. I actually saw that in a lecture once. This professor tripped over something on the podium, fell over, looked like he seriously hurt himself, but he managed to recover. He stood up again and a student raised the question, "Professor, could you repeat that step?" That was great. Okay, so now let's go this way, okay? So now we have C equals little circumference of little circle, circumference of little circle, capital C, circumference of big circle. Okay. So now, actually I should downgrade big L to what? Little l. Downgrade that. And now I've got to draw these blanks here. Here. So this is going to be big L1, and this is going to be, where is it? Ooh, this is going to be big L2. Okay? And so on. Got the picture? And this is going to be big R, and this is little r. Now, we're almost done. Because look at this little triangle. And look at this big triangle. What do you think they are? They're similar. They're similar triangles. So, these triangles are similar. We don't have to prove that. It's fairly obvious. It was obvious to the Greeks. These triangles are similar. That means, according to the principle that I just erased, their sides are, the ratio of the sides are in proportion. This means that L1 is to big R as what? As little L1 is to little r. This is to this as that is to that. Therefore, it says that little r, big L1 is equal to little L1 times big R. Now this is true for L2 and L3 and L4 and L5. So it says, suppose I add these up. So R L2 is equal to L1 big L2 big R. R L3 is equal to little L3 times R. And so on and so forth. Now, if I add all of these up, I get R times L1 plus R times L2 plus R times L2 to the n is equal to big R times little L1 plus big R times little L2 plus, I'm just using the system where I'm just not writing down these terms. If I have the chopping into 2 to the n parts, R times L to the 2 to the n. Or 8. You can put 8 here, as Jude says, if you don't like 2 to the n. But now I can factor this, because there's an R here. Simple algebra says that R appears in each one of these terms, so I can factor it. So this is L1 plus L2 plus dot 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 L2 to the n is equal to big R times L1 plus L2 plus L2 to the n. Now, I can actually multiply this by 2. Can you allow me to do that? Equals multiplied by equals are equal. Now by doing this, I get little d, which is the diameter of the little circle, right? And here I get what? Big